Do this action, got a couple practice to round out this chapter. This is chapter 6. Before we go on to chapter 7. Alright. Here's a typical problem where we're going to use the ideal gas law. Here's how I know that. There's one molecule and there's no changes. So pressure's not changing, temperature's not changing, etc. It's staying constant. This is a great ideal gas law problem. There's also a variation within it in that we're using density. So it's an ideal gas law that uses some variation. So for example, if you write this down, U equals nRT. And then we know a couple things. We know density is mass over volume. And then these are the most common variation formulas where you plug in density, or capital M is, in this chapter, it's molar mass. In the previous chapter, it's molarity. Okay? If you're talking about gases, capital M is molar mass. If you're talking about liquids, it's molarity. Alright, so we have, let's see what we have. We have temperature is 22 degrees C, and we'll need to add 273 to change this to kelvins. We also have pressure, that's 805 torr, and what we'll need to do is convert this to atmospheres in order to use it with the ideal gas law. So, on the back of your exam, you would see the following conversion: 1 atmosphere for every 760 torr. Why do we use atmospheres? That's to follow the units of R, which is 0.08206 liters atmospheres per mole Kelvin. So we need kelvins, which we have in temperature, moles, atmospheres, which we just calculated for pressure, and then liters. Let's see, we're not given the volume. Alright, so I want to do a little bit of kind of conversions here with my formula, and there's a number of ways you can manipulate the formula to get to where I'm trying to go. So this will just be one way. Alright, PV equals nRT. Let me divide by V and RT. So we've got P over RT equals N over V. Something like that. And now I'm going to make a little substitution for N. In this formula here, N is little m over capital M. So I'm going to plug in for N here. And the reason I'm doing all this is to kind of get density and things like this into the formula. Again, you could have tried it before, which has been fine. So here, it's little m mass over capital M molar mass divided by volume, or 1 over capital M, little m over V. What am I seeing here in the second part? This would be density. So this is 1 over capital M times density. Now I finally got density out of this. And let me solve for density, because that's what I'll want. Density, now to take the original part of the equation, is Pm over RT. Let's think about this for a second. I'll get a different color out in a moment. Density is what I want, so that's good. Pressure I have. Molar mass I can find because I have the compound right here. R is a constant, and T I have, so this is good. This is the formula I want, in this case in terms of density. So density will equal the pressure, which is going to be 805 divided by 760 atmospheres. The molar mass, you need to calculate from the periodic table, R, 0.08206, 0.08206, and then temperature, which is going to be 295 Kelvin from up above. If you do that, you'll get units of grams per liter, and that'll be 8.62. Okay, and that would be the density of halothane. Any questions on this one before we go to the next one? Okay, the next one is this one. Here, I had this up at the end of class last time, so we'll do it now. This is a typical Dalton's law problem. How do I know that? Well, if you look at it, there's more, it's a mixture of gases. When there's a mixture of gases, you're going to use Dalton's law, at least most likely. And here we have helium and oxygen. They're going to be mixed together in a tank. And we want partial pressure and total pressure. Dalton's law problem will ask for both or one or the other. So you'll either be asked for partial pressure, total pressure, or both. This is a pretty stereotypical Dalton's law problem. Oh, that wasn't good. Oh, that's worse. Okay, there we go. It'll come back in a second, I think. Otherwise, I'll just do it and you won't be able to see how I'm doing it. It'll be like radio. Okay. So, here we have a mixture of gases. If you follow on the flow chart at the bottom of page 52 of the reader, I'm going to follow that flow that I taught you, those steps from last time. The first step is I'm going to find the moles of each gas, so the moles of oxygen first. Since I'm given information related to the ideal gas law, I'm going to use that. So the partial pressure of oxygen, or the pressure of oxygen initially, is 1 atmosphere. The volume initially is 46 liters. R is a constant, 0.08206. Temperature initially is 25. Add 273 to that, you'll get 298 Kelvin. So the initial moles is 1.9 moles. And that's about 2. Now, I'll change pen colors and we'll do the same thing but for the other gas, helium. So I'm finding the moles of each gas using the same formula here. Initial pressure, 1 atmosphere. Initial volume given in the problem, 12 liters. R is a constant. And temperature is the same, 298 Kelvin. Okay, for this one I got 0.49 moles of helium in this case. My next step is to find the total moles. Let's do that. So I'll get a different pen color. Total moles is merely the sum of each individual mole. Okay, so that's equal to moles of oxygen, moles of helium. And this is going to turn out to be 2.39 moles total. Okay? So we've got all these moles now. Okay, now there's 2 different places we can go from here, but I'll just follow your flow chart. We're going to go to the mole fraction. So the mole fraction of oxygen is next. That's just the moles of oxygen divided by the total moles. Simply that. It's literally the fraction of moles. So for oxygen, that's 1.9 over 2.39. And I'll just leave it like that for now. Also, I'll do the mole fraction of helium, which would be the moles of helium divided by the total moles. And that is simply 0.49 divided by 2.39. And I'll leave that like that for now. Okay, the next step that we typically go for is the total pressure. Now, sometimes the total pressure is given, and you don't have to calculate it. But if it's not given, here's how you would do it. So the total pressure is going to be nRT over V, but because we're talking about totals, we want the total moles and the total volume, which is convenient. That's why we found the total moles earlier. N is 2.39 moles. R is the ideal gas law constant, same as before, 0.08206. Temperature is the same as before, 298 Kelvin. And total volume now is the volume of the 2 gases now in the final tank And if you look at the question, it says that the final, the tank volume is 5 liters. So we're putting two things together into a 5-liter tank. This turns out to be 11.7 atmospheres. So that's one of the things we want to find is the total pressure. Now that we have the total pressure, we can find the partial pressures, or the pressures contributed by each gas. So, the partial pressure of oxygen, doesn't matter which one we do first, is the mole fraction of oxygen times the total pressure. Or the mole fraction of oxygen, that's right up there at the top of the screen right now. 1.9 divided by 2.39 times 11.7 atmospheres is the total pressure. This turns out to be 9.3 atmospheres for oxygen. Let's do the same now for helium. Total partial pressure. Partial pressure of helium is the mole fraction of helium times the total pressure. And this is what we typically call Dalton's law here on the left-hand side. Partial pressure of helium is right up there at the top, upper right-hand corner. 0.49 over 2.39. And again, times the total pressure, 11.7 ounces. This turns out to be 2.4 atmospheres. And that's the pressure exerted by the helium in the container. Yeah?
Could you also, if you had the total pressure and then your pressure of the ocean, could you just subtract?
Awesome. Okay. There's some foreshadowing up here to exactly what I was going to do next. You could have said that the total pressure equals the partial pressure of this, all the gases. In this case, 2 of them. So notice these two numbers add up to 11.7. So instead of doing the second calculation, you could have said 11.7 minus 9.3, that's 2.4. So that would have been an alternate way of doing the second calculation. And totally acceptable. Okay. Any questions on this problem? All right then. One last example. We need to save a baby. Okay. So we're going to save this baby. You are the nurse on duty. You need to, again, it happens to be the same mixture of gases, heliox. You need to have the right partial pressures of oxygen so the baby doesn't have too much of one gas. And in both cases, helium is acting as what we call a diluent, something that dilutes the total amount of oxygen. So, this is, since it's a mixture, it's also a Dalton's law problem. It just has a slightly different setup. Okay? So let's take a look. Okay, we have 92.3% oxygen needed and 7.7% helium needed. You're the nurse on duty, so you get your calculator and your paper out. And you say, well, percent by mass, what does that mean? Well, you can just turn it into mass, say as a basis of 100 grams, and just say this is the mass of oxygen and helium. Okay, so you're changing your percent by mass into a mass by working backwards. Okay, and now remember, again, if you're following the flow chart, we need to start with moles. In this case, we don't have information related to the ideal gas law, so let's just do a conversion using the molar mass to get to moles. So this is a different way to get to moles because in this problem, different information is given. So in the case for oxygen, 92.3 grams, and it's O2, not just oxygen by itself, so it's 32 grams per mole. That's going to turn out to be 2.884 moles of oxygen. For helium, it's 7.7 grams. The molar mass is 4, and this is 1.925 moles of helium. Okay, we got the moles. Now let's go for the mole fraction. Okay, I'll get a different color pen out here. The mole fraction of oxygen is the moles of oxygen over the total moles. The moles of oxygen, 2.884, total moles, 2.884 plus 1.925. This turns out to be 0.599. Remember, no units for mole fraction. Mole fraction is unitless. Now let's do the mole fraction of helium. That's the moles of helium over the total moles. Which is 1.925 divided by 2.884. This is the total on the bottom here, 1.925. This is 0.401. Let's take a little pause for a second. What do you notice about those two numbers? They add up to 1, which if you didn't know, now you'll know. The sum of the mole fractions, in this case these two, will always equal 1. The sum of the mole fractions always equal 1. So instead of doing the second calculation, I could have said 1 minus this number will equal 0.41. That would have been an alternate way to do that calculation. Okay, well let's continue. The total pressure, in the previous example I used the ideal gas law to find it, but in this case I don't have that information. Luckily, the problem just tells me what it is. It's 730. And it gives me in units of torr. So that's just a given in the problem. Okay? In this case it's given, sometimes it's given, or it's atmospheric pressure, which would be 760 torr or 1 atmosphere. Alright, so finally we're going to get the partial pressure, so we can save this baby. Partial pressure of oxygen would be the mole fraction of oxygen times the total pressure. Mole fraction of oxygen is at the top of the screen right there, 0.599 times the total pressure of 730 torr. That makes the final answer in torr, which would be 440 torr. The partial pressure of helium is the mole fraction of helium times the total pressure, which will equal, right there at the top upper right hand corner, 0.401 is the mole fraction times 730 torr equals, in this case, 290 torr. Notice again that the sum of the partial pressures equals the total pressure. 290 plus 440 will equal 730. That means that instead of doing the second calculation, I could have said, oh, it's just 730 minus 440. So that would have been an alternate way to do the second question. Okay. Any questions on that? Yeah. And you can leave it in torr unless the question asks for something else, and I don't think it did. Let's see. Yeah, it doesn't ask for particular units, so just be convenient and leave it where it is. Yeah, so we're going to leave it in torr. Alright. I gotta zoom out on this one. You will see why momentarily. I just wrote a bunch of, if you want some practice problems, there's one on units. There's the gas equation summary, if you want to see a summary of equations. Solving gas law problems. On page 53 of the reader, and where is this in the textbook? Around page 217. Some Dalton's law problems occur over water, and it's a particular type of Dalton's law problem. I'm not going to do an example in class, because it's just another Dalton's law problem. But you might want to see it ahead of time, just so you see how they work. They're fairly easy. And then I've all kinds of solving Dalton's law. There's Dalton's law 1, or Dalton's law, then Dalton's law 2 and 3. Other examples. Okay, but while you're doing that, and those are all mentioned in the reader, I will just go check. We're about to start chapter 7. And just before I start chapter 7, I'll say the following. We finished all the gas laws now, which was combined gas law, ideal gas law, combined volumes, and Dalton's law. We also did gas properties, we did real gases, and we did the kinetic theory of gases. So that's chapter 6.